I think yes, and I think
And
one who should record would be I. Okay, I would record the meeting,
thank you.
but I don't know. Maybe I can upload the recording on Moodle later on.
That would be great.
Yeah, that
Okay,
would
no
be great
problem.
because we cannot record anything now because when I press the
Yeah,
record.
because the host is
Exactly.
the only person who can record
Yeah,
the
yeah,
meeting.
yeah, yeah.
Yeah, yeah, I would do that.
Okay, thank you.
Okay.
Tigranjan, what we are going to cover today?
Today we're going to like during the last session. Let's just start and let me share my
Okay.
desktop. Is it visible?
Yes.
Yes.
So okay, let's start. So last time we talked about some general ideas of classification, and we went through over this notebook where we discussed some decision boundaries, some uh, concepts related to confusion matrices, some accuracy matrix, etc. And today because there were like a few students present last time, today I just wanted to uh, go over really quickly one more time over this notebook and like to go through also the LDA QDA that you uh, had a class today, right?
Yes.
Uh, just a second. Mm, okay. So I guess it started recording. Okay. Last time we talked about the general classification method, and I showed how to use the make classification method to generate a sample including points from number of classes, that is 2, and we uh, we looked at the scatter plot of the data, and as we look now, we can see that there are 2 distinct classes. There are 2 distinct colors which correspond to different distinct classes. And because you didn't cover the logistic regression part during your ordinary class sessions, we just talked about logistic regression as one of the classification algorithms, and we use the logistic regression as our classifier to estimate the model accuracy, to understand what are the decision boundaries in our problem. And I showed the Python implementation of how to plot the decision boundary. You are actually not going to be asked about plotting the decision boundary during your midterm, but this is a good example of how you can do that. And like we understood that the logistic regression classifier is able to identify 2 distinct types of classes in our data, and the decision boundary in here identifies the borderline between those 2 classes. So whenever we try to predict using the model we have already constructed, and if the point is
Sorry to interrupt you, but there is like kind of background sound that really interrupts. I don't know.
background sound.
Yeah, yeah, yeah. It's like Yeah, that's gone. That's gone now. Yeah.
Okay, maybe that's my microphone. Is it okay
Yeah.
now?
Yeah. It is clear now. Thank you.
Okay, thank you. And we, w- yeah, we're talking about the decision boundaries, and we showed that the whenever a new point is observed, and the point, whether the point is the left side or the right side, our classifier will be able to classify it with respect to decision boundaries. And we also looked at the multi-class problem. We used the make classification method in here to generate data points, 500 samples.
Ներեք
Yeah.
մի բան էլի հարցնեմ։
Mhm.
Վերևում այդ decision boundary-ին logistic regression-ի ժամանակ դա նույն logit-ն է, չէ՞։ Այսինքն, եթե մենք ունենք մեկ predictor, տվյալ դեպքում սա y-ը հավասար է beta 0 գումաց beta 1 անգամ x-ն է, չէ՞։ Y-ի վերևի մասն է, չէ՞, հենց դա։
Հա, բետաներով գիծի հավասարումն է։
Հա, այսինքն ես էլ երեք փորձում էի Python-ում հիմա այս դուք որ վերևը տենց մի քիչ երկար գրել եք, այդպես հա պետք է անենք, կարծև չկա, որ ինքը այդ logit-ը տվի։
Ճիշտն ասած չգիտեմ, կարող է կա կարճ ձև, բայց ես չեմ փորձել։
Ես որովհետև coefficient-ները իրա վերցրեցի ու intercept-ը ու փորձում էի այդ կետերի վրա այդ գիծը տանել, մտածեցի կարող է այդպես հնարավոր լինի։ Չէ, ինքը x1 x2 չէր հասկանում, էլի որ մենակ մի երկու dimensional էր line-ը հասկանում։
Լավ, մի հատ ես կփորձեմ ուրիշ ձև էլ ճարեմ,
Հա,
ուղարկեմ։
չէ, ուղղակի ուզում եմ իմանալ դա հաստատ այդ logit-ն է, չէ՞։ Դուք ուղղակի ուրիշ ձև եք փորձել։
Հա, ուրիշ ձև եմ ես նկարել ստե ու multi-class-ի համար էլ and for the multi-class, yes, we generate in here the 500 observations or using the make classification method that includes three class types in our data, and here we can see three distinct classes, the distinct classes in the corners of our plot chart, and we also in here can use the same technique to draw the decision boundaries in here. But I guess we'll talk about your question a little bit later, Silva, right?
Yes, thank you.
Okay. And in here we also discussed some accuracy metrics that we use during our classification, during estimating the performance of our classifier. And for example, we took another example of make classification method and generated one 1500 points using three classes in our data set, and we made sure that the percentage of the observations belonging to some of the class is almost equal. And we use the logistic regression classifier to fit a model to our data, in which it took some parameters. The solver is the as you already know, the logistic regression beneath does solves some optimization problem, and it uses a gradient descent algorithm to find the optimal values of beta, and the solver in here is the LBFGS, which stands for which is an acronym of some names of statisticians. And the multi-class is equal to auto, means that whether if we are doing the multi-class logistic regression, the auto setting will understand and use the multi-class option of the logistic regression in here. And here we print the accuracy. And by saying the accuracy, we understand the ratio of correct predictions divided by the number of total predictions, and we'll talk about this a little bit later. And we also talked about the confusion matrix, and as you might already know, the confusion matrix is the following matrix, which represents the number of true positives, the number of false positives, true negatives, and false negatives. And this matrix is a good accuracy metric to estimate the performance of our model. And in here, as we have as instead of two classes, positive and negative, we have uh, three classes. This confusion matrix represents the actual values versus the predicted values, and the 0, 0, and 3 in here represents the number of correctly predicted observations versus the actual labels, and the second item represents the prediction results. um, I mean, our model said it belongs to the class 0, but it was actually class 1, labeled as class 1, etc. And the diagonal entries are the true 0, true 1, and true 2 classifications. And the accuracy in terms of confusion matrix can be defined as the sum of the elements in the diagonal divided by the total number of the sum of total number of entries in our matrix. And we also talked about the classification report in here, in which classification report method from scikit-learn, if I'm not wrong, from scikit-learn, yes, represents a classification method for distinct class types, and it says what how much precision does our model provide, what are the recall, F1 score, etc. And it provides some average statistics in here, and using this data we go deeper and estimate the performance of our model, in general the classification model, by using the ROC, that is the receiver's operations curve, and the PR, which is the precision recall curve, to understand whether our model performs good or bad. I mean, to get some estimate. And for
Sorry, this
yeah,
ROC and PR curves are the measures by which we can
yeah,
compare the models.
yeah.
Okay.
For example, for example, as you might have already known, the precision about the precision and recall. The precision is the ratio of the true positives divided by the true positives plus false positives, and it shows in general how many selected items are relevant in our model. And the recall is the ratio of true positives divided by the true positives plus false negatives. And the idea in here is that we, while taking account the precision, we want to understand whether our model is good at classifying the whether it is good as classifying positive as positive and not a negative. And the recall is interested in measuring our model's performance, whether it is good enough to find all the positive samples in our classification problem. And there are some other measures, sensitivity and specificity, in trying to understand the performance of our model. But the main two are the precision and recall, uh, and the F1 score, which is the weighted weighted precision recall dependence score that is used while we have a class imbalance in our problem, and while we let me while we try to like interpret the results of the ROC curve, we plot the false positive rate versus the true positive rate, and see how does this curve, which is actually a probability curve, explain our model. And here we're actually interested in the area under the curve, which is also which is in other words called AUC. And AUC represents whether our model is accurate enough, and it is quite, you can interpret it as the R square in the linear regression while we were doing, and AUC is quite some kind of 0 to 1 accuracy metric that we use to understand whether our model is good or not. And while we okay while we talked about the ROC curve and the AUC in here, we saw that we actually wanted that our false positive rate be minimal and the true positive rate be like higher. And in here we can see that so the ROC curve is plotted using the thresholds in here, and for each threshold we like estimate the model performance in our classification tasks. And in here we can see that uh, starting from this point, as our false positive rates gets higher, our true positive rate also gets higher, but not as fast as our false positive rate. And using the ROC curve and the threshold set in here, we're actually trying to understand the optimal threshold for our model. And and while we go deeper into understanding the balance between the classes, we look at the PR curve, which is the recall versus precision curve. And while doing a classification task, we always want to have the trade-off between recall and precision, and we don't want to have a high precision but bad recall, or the vice versa, low precision, the high recall. So using the PR curve for each class types, we in here try to understand what is to confirm our intuition that for some threshold in here, the recall takes a higher value and the precision is taking a higher value. So we talked also about the stats models library in here, and we like generated some points, and we showed that there is a possibility to use these stat models to construct a classifier and to solve a classification task, but the stat models is not so consistent, and we just know that there is a possibility, but we're not going to use that. And yeah, and today, as you had a lecture about the LDA and QDA, we we will like go through over the implementation details a little bit, and I will show how the LDA and QDA can be used to solve the classification tasks in the default CSV mentioned in the default CSV problem. And this CSV file and the rest of the IPython notebook files is on Moodle. You can download it from here, and this is the default CSV. And okay, as you know, the LDA and already know the LDA and QDA are another algorithms for the for solving a classification task. And despite the fact that the logistic regression LDA and QDA solve the same task, we know that the logistic regression is pretty good when we have a binary classification problem, and the LDA QDA are good when we have more than, like in average they perform better when we have more than two class types in our data set. And yeah, so we're going to use the scikit-learn library in here, and we read the CSV defaults, and while we print this CSV in here, the header of the CSV, we can see that we have some observations from features, and we have non-numeric values for default, for students, for balance and income. I don't really know much about this data set, but I can really understand that we are going to solve some classification problem, and we are going uh, to classify whether student with a corresponding balance and income will go to default. And while we try to get rid of this non-numeric values, we use the get dummies method from the pandas library, and we convert the no and yes values into 0 and 1 in here. And we want to understand as our response, and here is default yes. We want to understand whether there are more than two classes in our default yes met response feature. And we use the numpy unique method to understand that, and we can see that the number of unique classes in our default yes is 0 and 1. So we are trying to solve a binary classification model problem in here. And for some statistics in here, we might want to understand how are the values in our for the student yes, 0 and 1 observations, the balance how the balance values are distributed. And while plotting the box plot using box plot in the pandas data frame, we haven't used this before, so this is new way of plotting some box plot on our data. We can see that there are some outliers in here, and the median is around like 750 for the students, for the people who are not students actually, and the median is around 1000 for the people who are students, the balanced median. And this is another familiar way of plotting a box plot using the Seaborn library, and these two correspond to the same result. And we want to understand whether what are the balance of those people who went default, and yes, went default and didn't. And we can also see that the median for the zero class in here is around also 750, and for those who went default is around like pretty higher than the for the students observations, around 7050. And using the Seaborn library in here, we try to plot the balance versus a income chart in here. We use y as an income, x as a balance, and we give an input the data, dummies data that we have created above, and we can see some uh, orange points in here and the blue points in here, and our problem possibly is the one to build a classification model using the linear discriminant analysis to be able to classify those who will go default and who will not. So I guess after 6 minutes, we should all re-log into Zoom so we can continue our meeting. So be aware that this might like throw us all out of the meeting. Yes, and
is for is related to logistic. What's LM plot?
it's what?
LM plot.
Implode?
Yes, it's for classification. This
It's actually, we're not like plotting in here some decision boundaries or some classification plots in here, but we're just using the LM plot to get the visual interpretation of our data in here, and to see that we actually have orange and orange points scattered around these blue points. This is just a way of plotting this income, balance versus income. You're actually free to use another library if you want.
And can we know that from this plot that the classification is linear or not linear?
From this plot,
Yes.
I guess,
No.
uh, I guess there is no. I guess you cannot actually. You have to try. And from this plot, I think you cannot understand whether LDA or the QDA will work better on this, whether the linear or the quadratic classification method will work better on this data.
Thank you.
Thank you. And while we using here, while we try to generate, like reconstruct X, which is, and here the balance, income, and the student yes data frame, and the Y, which is which are the classes, corresponding classes in our classification problem. We use the linear discriminant analysis in here that is imported. That is a method from the scikit-learn library from discriminant analysis class. And you can also see that the import for the QDA is similar in here. And we initialize a linear discriminant analysis object in here, that is the small letter LDA, and we use the LDA.fit to fit LDA model to our X and Y. And while we print the model LDA to understand, like to confirm one more time which method are we using, which classification algorithm are we using in here, we can see that we use linear discriminant analysis, and the model score in here is 0.97. So the model score represents in here the accuracy that we talked about, and it's the sum of the true positive and true negative values over the uh, total items, the sum of total items in the confusion matrix. But you might have already learned from the class sessions that the high model score or model accuracy score does not might not actually represent a good model performance, and we should really look on other accuracy metrics, because who knows, we might have some class imbalance problem in our classification that our model scores a high accuracy, but it is not actually good enough at classifying the rest of the class types. So we're actually going to be disconnected, I guess, in just a minute. So okay, and with as last time we also talked about this, that we have some model.predict and model.predict proba methods in here, and the difference between predict and predict proba is that proba will return the probabilities of the observation to be in class 1. So this is a probability, and this is 1 minus of the probability that is actually the probability of the observation being belonging to the other class, and this is about 0.99, and this is really pretty close value to the 0. And the pred is just pred just returns the class types. I mean, instead of probabilities, it returns whether the observation belongs to 0 or 1 class. And as in here, we կեսը մնացել են մյուս meeting-ի մեջ։ Չորրորդ լսում եք դուք ինձ։
Այո,
Մի քիչ սպասենք էլի, ոնց որ այն մնացածը կորան ճամփին։
այդքան շատ են։
Հա մի 18 հոգի կար։ Քեզի կորան։ Մի 5 րոպե սպասենք, չեկան ոչինչ։ Էլի դասեր ունեք դուք Zoom-ով։
Հա, լրիվ դասերը Zoom-ով անում եմ։
Բայց բոլորը անում եք։
Բոլորը, անպատասխան։
Լավ չի։
Չէ,
PSS անում եք այդ Zoom-ով բացի իմ դաս։
հա նոր OP ենք անում։
Հա, օփին։ Զառան, հա, օփին դասավանդում։
Բանա, Ստեփանիա։ Ճանաչում եք Մոնիկային։
Մոնիկա, չգիտեմ։
Ու Եվա։
Մոնիկան բան է, բայց network-ի TA-ա, չէ՞։ Թե դասախոսա։
Չէ, բանը,
Instructor-ը։ OP, հա, չեմ Այսինքն կարող է ինքը երկու դասի TA-ա։
Կարող է, կարծում
Մի
եմ,
հատ էլ բան network կամ ինչ-որ communications տենց մի բան։
կարող է ինքը շատ դասերի TA իմանալ որ կա։
Հա, ճանաչում եմ ուրեմն թեթև։
Խոճուճ մազերով աղջիկ։
Հա, թեթև, բայց անձամբ չեմ ճանաչում։ Լավ, ինչ ասեմ, եկեք սկսենք։
Լավ։
Ավելի շուտ շարունակենք էլի։ Հիմա էլ է շուխուռ իմ բանի մեջ, մայքրոֆոնի մեջ։ Հենց լինի ասեք էլի։
Այո, հա, կաս։
Okay. Okay, let's continue in English. Do you see my screen now? Okay. Right. And we were in here. And okay, while we perform the LDA in here, we would like to see, and let me just record. Okay, while we already constructed our model using the LDA, linear discriminant analysis method from scikit-learn, and we saw that we have some accuracy of the model 0.97. Would like to know what is the representation of the confusion matrix in here, and what we can understand by looking at the prediction accuracies derived from the confusion matrix. And to plot the confusion matrix, like in last time I showed that we can use the plot confusion matrix in here. Just a second. We can import the plot confusion matrix from the scikit-learn and use that, and use the method to plot the confusion matrix of the classifier. And here also we can use the plot confusion matrix, and we can this is really optional. This is really optional. This is the Python definition of the plot confusion matrix, and this is to show how does the plot confusion matrix work beneath. And you can just read this for yourself, and there is no extra thing in here. It just takes the same values, and it uses just the normalized true or false flag in here to understand whether we would like a normalized confusion matrix or not normalized one. And in here, it just uses the plots and subplots to plot the confusion matrix. So while without loss of generality, in here, we would like to understand the true negatives, false positives, false negatives, and true positive values of our confusion matrix. And that's why we use the confusion matrix from scikit-learn. Just a second. From the scikit-learn matrix library, we use the confusion matrix method to evaluate the true positive, true negative, etc. Values from our confusion matrix, and to plot those and to understand what do these values tell us about. We just look at the matrix form of the confusion matrix, in which here is the visual representation of the confusion matrix, and we see that we have this is the true label, this is the predicted label, right? And we see that the true positive rate is extremely high in here, despite the fact that the rest of the true negative, true false negative, and false positives are low. And what can we understand from here is that we might have some class imbalance problem, and the accuracy in here that is concerned with that is 0.97, and we might thought that this is a good accuracy. We can understand, perceive the idea that our high score of our accuracy can be connected with the problem that we have a class imbalance problem in here, and we have a lot of observations from one class, and we don't have so much observations from the other class. And in here, we can see that as the label was zero, our model was able to classify 9,645 observations as zero, and as the actual label of our observations was 0 and our model misclassified it as 1. The rate is 22 and you can see that the actual label is 1 and our model predicted as 0 is 254, etc. And to not be misperceived by the results, we should look also at the other accuracy and performance measurements of our classification problem, and that's why we use the classification report in here with respect to six-digit roundation. And we can see that, for example, the precision for the class 0 is pretty high, and the recall is also pretty high for the class 0, and the F1 score is really, really good in here. But what is really stressful and disturbing is that although the precision is not so low, it's 0.78 in here, the recall actually is pretty low, and we will just in a minute see the precision recall curve and like understand that our model is really good at classifying one class and really bad at classifying the other one. And we can see a really bad F1 score in here. And to just note being satisfied by those results only, we go through by plotting the ROC curve, the receiver's operations curve in here, and which is this one, which plots the false positive rate versus true positive rates. And we can see this is for just one class where the label is equal to 0. And we can see that the area under the curve, that is the area under the curve, is pretty, the measure is pretty high at 0.94. So our model is pretty good at identifying these 0 class entries in our model. And while we want to know the receiver's operations curve for the class 1, we see that our model is even worse than the random guess. So this orange line, which is y equals to x line in here, 45-degree line, this is when we see a ROC curve around this line, we can say that it is neither good nor bad than a random guess. But while we see a ROC curve beneath this line, we can really, really strongly state that our model is not good enough to classify a small number of classes that correspond to 1 in our model. So despite the fact that we have a high accuracy score, this is an example of class imbalance problem. And while plotting the recall precision curve in here, we can see, just a second. We can see that something is not right in here. Yeah, this is the precision recall curve for the label 1, and we can see in here that as the recall gets higher, as the recall gets higher, the precision is depleting in here, and this is no ordinary situation, and the AUC, the average AUC in here, precision score, I mean, is 0.53, which is which is around the average random guess. So
Excuse me,
I
can
just
I ask a question?
yeah.
In the computer matrix, for drawing computer matrix, what's normalization? It's the normalize the data. What's this?
Normalization is when you're scaling your matrix entries around 0 to 1. I mean, here the scale is from 0 to, I don't know, 10,000. Normalized confusion matrix contains values in here that are scaled from 0 to 1.
If we don't do that, if we don't that,
But this is just a data science perspective. One would like to see the normalized values, the other one would not. This is just a matter of taste.
and about the drawing rock curve or
Yeah.
we FPR TPR threshold. How what's this called? FPR then TPR.
FPR is the false positive rate.
Yeah, I know.
TPR is the true
About the
positive
code.
in here.
We call yes, we call rock curve method, and we assign it to thresholds TPR, FPR.
We're assigning y true is the actual labels in here, y score as the predicted probabilities of our classes, and the POS label is equal to 1, means that we want to plot to get the corresponding values, the FPR, TPR, and the thresholds for the label 1. And while we print those in here individually, you can see a huge matrix in here, and for each threshold, I mean, it's actually the rock curve in here actually tries to estimate the false positives, the number of false positives and the true positive with respect to some threshold, right?
Yes.
Here is the, for example, in here, let me show it in a good example.
So the result
For
of
example,
rock
here
curve
yeah.
is matrices, and we assign it to FPR, TPR. Yes. I can't understand. The result of rock curve.
Okay, I see. The rocker method returns 3 values, and those 3 values are the false positive rate, true positive rate, and threshold. We're actually not using the rock curve in here to get this plot. We use the false positive rate, true positive rate, and thresholds to plot the rock curve using those values in here. So the rock curve actually shows for each threshold, for example, threshold, for each threshold value, the true positive rate and the false positive rate in here. And we have a lot of thresholds in here, and we want to understand what is the optimal threshold right in here. And the optimal threshold is the one that provides a higher true positive rate in here and the lower false positive rate.
And we also create the thresholds, or it's default?
No, it's default. No, it does everything. And I just wanted in here to show that that what refers to the logistic regression that we have done previous in the maybe we didn't do that, that was left, but in here the problem is the same. We're taking the default data and we want to build a classifier, this is exactly the same problem with different solution. In here we use the logistic regression approach, and here we use the LDA. So later you will see the QDA approach on the same data in here, the QDA approach on the same data. And I just wanted to show that despite the classification method we choose, we're actually getting similar results. And here we identify also a class imbalance, and we can see that the true positive rate in here is quite the same as the true positive rate in here, because 9.6 plus 9.6 times 10 to the power of 3 is actually about this value, around this value, and the rest are also similar to each other. And despite the fact we might have some good log curve for the class 0 type, and the good accuracies in here, if I'm not wrong, yes, in here we have 0.96 accuracy score. Yeah.
Մեկ երեխեք ասում են քեզ են սպասում, բայց չգիտեմ որտեղ։ Մեկ պակասվում, ասում են որտեղ են ձեզ սպասում։
Oy, cool.
Մեկ Ալո։
Հա։ Ասեք նույն բանով, նույն մոդելի լինքով։
Հարու ժամը։ Նույն տեղին կպեք։
Նույն մոդելի բանով,
նույն մոդելի տեղով։
Հա։
Ինչպես չէ կարող։ Մենք արդեն 10 րոպե սկսել ենք, 15 րոպե սկսել ենք։ Ինչպես չի լինում, այսինքն host չկա, կտրում եք host չկա։
Լավ, մի հատ հեսա meeting դնեմ շուտ մոդելում։ Հեսա դնեմ թող կպնեն, օքեյ։
Հա, լավ։ Այս լիվան ենք, այս meeting-ը։
Եկեք լիվ անենք, նորը դնեմ, հա։
Լավ։ Աթե նոր meeting-ը ուզում Լսում ես։
Աչքիսան հինն են
Որտեղ մտնենք։
Հա, իսկական է։
Չգիտեմ։ Գրում է in progress model-ի։
Ժող մի link չի ընդհանրեն, այդ link-ը։
Հա, մի link-ը։
I don't know, ես refresh
Կարող ես LDA QDA-նա։ Այդ մենակ էսա գրում in progress։ Ես ես virtual PSS 7 դա եմ։
Էլի էս նույն սաստավով ենք։
Երեխեք կարող է կապ virtual PSS part 2, երևի տեղ պետք է մտնենք։
Տենց բան էլ կա։
Հա, ոնց որ նոր է ստեղծվել, մենք երևի այն առաջինն ենք մտնում։
Հա, հեսա։
Հա, մենք
Էդի refresh անենք, որ երևա չի երևում։
լավ։
Пока։
Սասալ part-ուն չի։
Էլի մենք
Ճիշտ տեղում ենք։
հա ոնց որ հիմա հա հեսա ոնց որ Տիգրանն եկավ
Ինչ որ dimension-ներում travel ենք
Հա,
անում։
լրիվ է դա։
Կարևորը Տիգրանն
Մենք քեզ
տեղա։
փոխում ենք ժողովուրդ ձեզ։
Մենք էլ ձեզ։
Եթե Տիգրանը
Մենք
տեղա ուրեմն
կորել ենք ինչ որտեղ։
Բայց ոնց որ մենակ չէ, էլի, ես կպետնի։
Հա, Արամեն
Ես
ասաց, որ դուք մենակ չեք։
Այս մտածեցի տենց թռնասախ։
մենք են նույնն
Մենք
ենք
էլ հակառակն ենք մտածում։
Հա, ես հնարավոր է թռնեի։
Ինչ որ բան չեք արել, չէ՞։
Արել են։
Չեմ արել ոչ բան։ Հա, արել ենք, մի
Ոնց
20
արել
րոպե
են։
խոսում ենք։
Իսկ
Հա,
այս
ոչինչ, արագ
record լինում է, ձե դուք record եք անում, հետո post-ալու եք։
Հեսա արագ բան կանեմ, կանցնենք էլի ինչ որ խոսացել ենք, լավ չէ, արագ չէ, դանդաղ
Որ
կանցնենք։
առանց այդ էլ արագ է, այն որ սենց սովորական դանդաղ անցնում է, այդ արագ է արդեն։
Հիմա ինչ անեմ։
Մի հատ էլ վրից արագ, չգիտեմ։
Հա, մի քիչ դանդաղ կանցնենք։
Մի հատ հարց էլի դուք record անում եք, այս պետքա հետո։
Էդ էի ասում բանը, առաջ ոնց որ միջև այս պահը արել եմ, հեսա մի հատ էս խոսանք բրցնենք, share անեմ ձեր հետ screen-ը, ատեն անում եմ, նորից record անեմ։
Դրանից էլի լինում է, չէ՞։ Record։
Հա, բայց երկու մասով ալնելու կկպցնեմ իրար։
Չէ, պետք չի կպցնել։
Չէ, ինքը zip չի անում, պետքա կպցնի։
Բաները էլի, այդ երկու recording-ները կկպցնեմ իրար։
Okay. Thank you.
Լավ, okay։ Որտեղ էինք ասե, հա հիշեցի որտեղ էինք ասե։ Ստեղ էինք ասե։ Okay. So in here, like when we printed the mode LDA and the mode LDA score in here, we see that we're using the linear discriminant analysis method and our model score is 0.97, right? And by looking at the 0.97, we might think that our model is a good one, but what does 0.97 mean? It's the number of true positives and the true negatives, the sum of the true positives and the true negatives divided by the all entries of the confusion matrix. And we will later see that this model score can be actually a little bit contradictory. And to predict the x values by the LDA model, we use the dot predict x in here, and the difference between predict and the predict proba is that the predict proba returns the probabilities of the item to be in a class 1. In here, this is the response of the model dot predict proba x, and we can see that this is the probability, like two probability values next to each other, and this vector, this column actually indicates the probability of the ith observation being in a class 1. So this is quite almost equal to 0.97. Sorry, 0.997, and this is a pretty close value to 0. And we can the threshold actually in our model, like for example in logistic regression, if the threshold is for example 0.5, the model uses this probabilities, and it looks like, for example, if we got for example, above threshold value for the item to be in a class 1, then it is in a class 1. And the same principle is applied in the LDA and QDA. And to go further, I showed, like in last time we so this is the same problem we discussed in using the logistic regression classifier during last problem solving session. And there we use the plot confusion matrix from the scikit-learn to plot the confusion matrix. And here, this is the Python implementation of the plot confusion matrix. So you may take a look to this code if you want. This is just an optional. And by applying the LDA on our data, we might want to get the confusion matrix output that are the true positive, true negative, false positive, and false negative rates. And that's why we use the confusion matrix, give the actual y values as a first input, we give the predicted y values as the second input, and we use the 0, 1 labels as our label set. And while we print the confusion matrix in here, we can see, so this is the visual implementation of the confusion matrix. We can see that we have this axis represents the predicted values. These are the actual values, and we can see that for example, the model is really good at predicting 0 labels, because in 9,645 cases, the observations had the actual label 0, and our model predicted classified them as 0. And while we are happy with this true positive rate, we can notice that there is some imbalance between class types. So while in here the 0 is the actual label is 0, and in here the actual label is 1, we have a class imbalance between the data observations belonging to class 0 and the class 1. And we understand in here that the high accuracy score that we experience while performing LDA is a result of the class imbalance problem. So our model is pretty good at classifying zeros as zeros, but it is not quite good at classifying ones as ones. And while we look at the classification report, which is a method from the scikit-learn, we can see that we have pretty good precision for 0 label classification. We have pretty good recall score for 0. We have the pretty good F1, which you might remember is the 2 times precision times recall over the precision plus recall. And this is a good measure to what we're trying to search a balance between precision and recall. And while we look at the precision of our model's ability to classify ones as ones, we're actually not satisfied in here though, because we have 0.78 precision score, which is better than the random guess, but this is not good. And we can see that we have really bad recall score in here. And sorry. and we have a really bad F1 score in here, and by 0.23 recall, it is just saying that our model is not able to find all the positive sample. I mean, in here the samples belonging to the class 1, and low precision shows that our classifier is not able to not to label a positive sample that is negative. And well, to understand the how does the ROC curve inform us about this class imbalance problem, we use the ROC curve from the scikit-learn, and to receive the false positive rate, true positive rate, and thresholds. And the plot in here for the label 0, which was the uh, prevalent class in our data set, we can see that we have a ROC curve, and we have the large area under the curve, and the area under the curve, which is AUC, is equal to 0.94. And we are really happy in here with this situation. So we're saying that our classifier is good one at classifying zeros. But while we try to look at our classifier's false positive rate versus true positive rate for class 1, we see that the curve is even under the 45-degree line, which is the line for almost equal to random guess classification. And we can see that as the false positive rate, the true positive rate is getting higher as the false positive rate is getting higher, and we can see that the area under the curve should be really small, and our model is not able to properly classify the data points belonging to the class 1.
I'm sorry, in which case was this, the second drop curve?
Which what?
Didn't get. The second drop curve was in which case? How did we get this one, this plot?
Yes, in here, I just changed the POS label, which is used to get the false positive rate, true positive rate, and threshold for the label 0. So I'm just getting the same false positive rate, true positive rate, and thresholds for the class 1. And in here, while I plot, I get the ROC curve for the class 1. I mean, we should have two different ROC curves, right, for individual classes.
So we don't estimate the accuracy of a model, but the accuracy for each class, right? Not the whole model, but for how
we're
the
actually, you're right. We're actually trying to look at the accuracy in here. For example, if we had, if we had 0.2 in here, this is really bad. That means the model, we're free not to look at the ROC curves, etc. While we see those kind of accuracy, but the accuracy itself, the high accuracy itself, does not propose a good model. So
class imbalance.
we're trying to look at classifiers performance at classifying each class type data points, and that's why we're looking individual ROC curves in here for different classes, and we find out that the ROC curve for the class 1 is not a good one, and we have low AUC in here. And further, we can make sure that our model is not good one at classifying the label ones by looking at the precision recall curve. And that's why we use precision recall curve method. I don't know what's happening in here, but we use the precision recall curve from the scikit-learn to get the precision recall and threshold of our model. And this is also for label one. And while we plot it, we see that as the recall gets higher, the precision drops down, and the vice versa. And the precision recall curve is actually the case where we want to have to get the trade-off between precision and recall, and we want to have both a good recall score and a good precision score. That is, we want our classifier like not to label as positive a sample that is negative, and we want our classifier to find all the positive samples in our class. And here we see that this is actually no better than the random guess classification problem. And the average precision score is 0.53. And yes, we talked about proba. And in here, I just wanted to like make comparison with the logistic regression example that we looked at during last problem solving session. This is the same data, and the same task is solved using the logistic regression. And we can see the similarity between confusion matrices in both classification methods. Here we have 96.45 true positive rate, and here we have almost equal true positive rate while using the logistic regression as a classifier. We can see a high ROC curve, a good ROC curve with 0.91 AUC for our, I guess this is for the class 0. And we can see a similar precision recall curve that we had, similar to this one that we had in the LDA model. And while looking at the classification report from the scikit-learn, we're convinced that we have similar class imbalance. So this scores just differ from method to method, but the general idea that two classification reports try to make us understand is that our model is a good one for the classes, for the data belonging to class type 0, and bad one for those belonging to 1. And yes.
In the report, for the class 0, we have precision 0.9, and both precision and recall for class 0 are high.
Yes.
What that means, for example, it's good, yeah, for
that is our classifier. Our classifier is really good at finding the at classifying the data belonging to class 0, and not only it is also good at finding all observations belonging to that 0 class.
But for class 1, it's not good because recall is
Yeah,
very...
but for class 1, it's not good because both precision and the recall are low. And from confusion matrix, we can see that as a true label was 1, there are about 270 data misclassifications by our model, and actually the total number of entries, the total number of observations belonging to class 1, they're actually not so much, and the vast majority of them is misclassified by our model. And
one more question.
Yes.
So what would be the ideal precision recall curve? Like, I know that we want both to be as high as possible, but we want it to perform better than the random guess. So should it be like above the line?
It should be like something like this. Let me let me show a good example in here that we had. No, not this one. Let me just quite something like this is a ROC curve.
Yeah.
This is a ROC curve, but this is a precision recall curve. So we're actually in here. We're actually we want the picture is not a good one, but I can explain the idea. So for each class, we want to have a higher recall and a higher precision. And for that, a good representation of PR curve is the one that has this kind of shape. And we can, for example, find some optimal value between. So these are these two curves belong to, for example, to 0 and to 1 class in our data, and we are trying to find some value, some threshold value in here for which the recall and the precision score relatively adequately high values.
Okay, thanks.
But there is no explicit way to define what is a good good precision and recall curve or accuracy for us, because sometimes, for example, there might be a case when we are sure that, for example, we want our classifier to intentionally be good at classifying, for example, 0 class, because we know that the 0 class is very important for us, for example. But
yeah, it depends on the problem.
Yeah, it depends on the problem. But in general, we're trying to overcome this class imbalance problem, and yeah, that's all. And what refers to QDA, this notebook is quite similar to the one for the LDA, and the quadratic discriminant analysis is one of the other classification algorithms that, if I'm not wrong, you have discussed today during your class session. And the structure of the notebook is quite really similar to the LDA, and possibly the only difference is that instead of building a model using a linear discriminant analysis, we use quadratic discriminant analysis in here, while we construct an object in here, QDA. And we also in here make sure that QDA provides a high true positive rate, and we also identify the same class imbalance problem in here because the data is the same, and there cannot be a case, for example, if logistic regression for an optimal threshold provides a better result than the LDA or QDA. I mean, not better, but drastically different. And we also in here see that the precision for the class 0 is high, the recall and the F1 scores for the class 0 are high, and we identified that the same accuracy matrix for the class 1 are low, and this ROC curve for the class 1 using the QDA is quite similar to the LDA. And while we plot the VOC curve for the class 1 using the QDA, we see that we have quite similar results that we perceived in the LDA classification problem, and we understand that no matter the classification algorithms we use, if there is imbalance in our classes in the data, we're always going to score quite similar outputs in terms of classification. So I uploaded these notebooks, and this is from the PSS 6.
I'm sorry, what what comment could we make on the recall precision plot here?
In here,
Mm-hmm.
that is actually the same as it was for the LDA. And in here, we can see so we want to have a high precision and high recall, right? But that is quiet. We're trying to find something in here because we want to recall to be higher and the precision to be higher. So for this case, we see that for either the precision is low or the recall is low. I mean, we cannot have, for example, 0.8 precision and have 0.8 recall, because either recall is bad or the precision is bad. And in here, we, as our model is not good enough at classifying the data belonging to type 1, we can say that this is just no better than the random guess of the class type for the class 1. I mean, if you took for example, if you took all the class 1 observations and wanted to understand whether they belong to class 1 or not, if you randomly classify them as class 1 or class 1 not, the precision and recall actually should be this kind of similar.
Okay, so we simply should either choose precision or recall, given what is more important, to classify all the ones as ones or not classify wrong, and that's it. So my question is, what should we answer on midterm if we are given
if
such?
you're interested, if you're interested, what should you answer on a midterm? If you have this similar situation, you and you showed that we have a class imbalance problem, you can state that from precision recall, we also see that our model is not a good one at providing higher precision and higher recall, because it is not good one at classifying ones as ones, and I think that's enough. But as a solution to class imbalance problem, that is not in the scope of, for example, your midterm, people usually try to artificially, for example, artificially increase the number of class observations that are not present. For example, a solution would be in here to a solution would be in here to like artificially increase the ones, the observations in ones. For example, I don't know, to generate, to add from another source, to make quite a balance between those two class observations, and they would I think definitely improve the PR curve for the label one. But this is just an idea. I mean, you could just state that, yeah. Yeah, go ahead.
Okay. About this class imbalance, does the threshold does it have something to do with it? For example, if instead of 0.5 we take let's say 0.3, is it gonna change anything?
I mean, in ROC curve, let me show. So the ROC curve is actually a probability curve, right? In here, and it shows the false positive rate versus true positive rate for different threshold values. And for this class 1, we want to have a lower false positive rate and higher true positive rate, right? And the model itself decides this threshold. For example, let's choose this threshold to be 0.8. 0.8 for the class, I mean, not for the class, but 0.8. And as we want the true positive rate to be higher, we cannot change this 0.8 from class to class. I mean, we always choose this threshold with respect to our model's ability to have lower false positive rate and higher true positive rate. And whenever if I'm not wrong, the question was if we change the threshold, would this overcome the class imbalance problem or not? The answer is no, because when you change a threshold, the data itself doesn't change in there. And for example, you might get what you want to see in the accuracy matrix, but you might start to classify very badly zeros as well if you change the threshold.
Okay, thank you.
Thank you.
And I'm sorry, it's me again. What about homework for 5?
Homework 5.
Will we get the document Python code for this, or we should come up with the code based on the?
I mean, I haven't looked at the homework 5 yet. Just homework 5 is about the logistic regression, right?
Yes.
I think the PSS is enough for you to besides the problem 5, the rest is actually from the PSS 6, I guess. And I think
any chance we could get the code in a structured way for the homework 5, because I was not present, and I guess many of students were not present, and the code was too heavy to get what is actually required, what is a plus, what is needed, and what's not.
I'm not sure, but I will do my best to provide the structured version of homework 5.
That would be really, really great. Like before the midterm, you did that way.
Okay.
Thank you very much.
Can we have a PSS, for example, next week, and we do
yes, we're
an
going
example.
to have.
Yeah, and we do an example of logistic regression for data set. Just one example.
For data set, I mean,
Yeah.
I mean, we have this example with the default CSV data in here. You want one more? I mean,
you mean it's okay? It's enough, yes. Is it enough?
Because I mean, I'm pretty good at this idea, but if I think your midterm is pretty close. I mean, in April 4th, right? And maybe there's some topics that we might not be able to cover if I'm not sure if we have time. I'm really okay with that.
I think if we have the solutions for the homeworks in the structured way without extra code, so that we won't be so we don't so we are not confused, it would be great. It would solve.
Yeah, I think you're right, but the worst part in providing you with the final structured way of homeworks is that sometimes I'm really okay with that because as a result it's you that are learning. Sometimes in the midterms we see copy pastes and people sometimes do not understand what they're copying. But I mean, I'm not the instructor, and I'm really okay with the idea of providing you the structured way. But my my recommendation is just like try to understand possibly what you are doing and try to ask a lot of questions because I would like you to understand it wholly before implementing. Okay.
Can I ask a question about the last midterm?
So yes, we have 2 minutes before the Zoom disconnect.
I'll be fast. Yeah. So like, are we not supposed to copy any code at all? Because like, for example, for the how I don't remember the names, but for those like 4 graphs,
yeah,
you already had the code. So like,
yeah.
For example, I copied it like with understanding, like all my midterm, whatever I have, I understood what I'm writing. But I didn't think that we are not allowed to copy anything. Like,
yeah, you're actually entirely allowed to do what you think you can do, but the idea was
points for that.
You what?
Is he gonna reduce points? The instructor, is he gonna like?
I mean, I wasn't checking your midterms, and I think he told you that if he doesn't find any summary or explanation, you might get 0 for that.
Yeah, but if we have the explanation,
yeah, that's fine.
It will be waste of time to like write it again if you already have that part, like for example for graphing or something.
Yeah, that the graph part, etc. is fine. I mean, I will try to do my best to provide you with the homework solutions, but I cannot say the exact date for this structured file, but I will try to do as soon as possible.
Okay, thanks.
Okay, thank you guys.
Thank you.
Stay healthy.
Thank you.
Thank
Bye.
you.
Thanks.
You too, bye.
Thank you.
Bye-bye.
Goodbye.